So chapter 4.3 is about solving recurrence relations using the substitution method. Substitution. So since this problem is a part of chapter 4.3, we want to use the substitution method to solve this recurrence relation. So the solution to this recurrence relation is already given to us, which happens to be big O of n squared. So what we're trying to do is we're trying to show the necessary steps and prove that the solution to this recurrence relation is big O n squared. So how do you do back substitution? So let me just copy the function that was given to us down here. So the first step of back substitution is plugging in the recursive function into itself. So what would be the result if we did that? So every time we see an n, we just replace it with n minus 1, since we're just plugging the recursive function back into itself. So this would be t of n minus 1 minus 1, and then plus n minus 1. So this solution that we got is just t of n minus 1, which is just this part. So when we simplify that, we have to keep in mind that this solution plus n minus 1 doesn't end here. We have to bring whatever was left at the top down like this. So now we end up with another recursive function, and we just have to plug this into itself again. So what is t of n minus 2? Well, we plug in n minus 2 every time we see an n. So n minus 2 minus 1, and then n minus 2. And then we simplify that on the left-hand side. So we keep doing this until we see some sort of pattern. So we've only done this recursive call twice, so we might need to do one or two more to gain an intuition as to what's going on, to see a pattern, because we need a general pattern to get a solution, to get a big O. So t of n minus 3 plus n minus 2, this part is just t n minus 2, which is this part. So we have to bring all the rest down. So when you bring it down, you might not see a pattern until you have some parentheses here. So I could do one more recursive call just to make sure. So what is t of n minus 3? So we have another recursive function, and we're trying to find the solution to that, which is t of n minus 3 is equal to t of n minus 3 minus 1 plus n minus 3. So t of n minus 4 is equal to, sorry, it's not equal to, t of n minus 4 plus n minus 3 plus n minus 2 plus n minus 1 plus n. So the pattern that we see here is that this increments, this is 1, 2, 3, 4, it increments until it hits some base case. So the thing about these recursive functions is that the recursion doesn't continue on forever. It doesn't just keep calling itself an indefinite amount of times. It stops at some base case. So we know that this recurrence relation is going to stop at some point, but we don't know exactly when. So we'll just say that it stops at some point I. So if we rewrite this recursion using I, we can say that this recursive function stops at n minus I. What's before n minus I? Well, it's just I minus 1. So plus n minus I minus 1. And then we have all this middle stuff here, and then it ends in n minus 2 plus n minus 1 plus n. So what is this endpoint? Well, it just equals 1. Unless you're given a base case like t of 1 equals 4, we just assume that it equals 1 because it's simplest. It's just a constant, and when we do a big O later, all the constants just get stripped out. So we'll just be using 1 for this example. So n minus I should equal 1. And we need to get a solution for I, so we'll just solve this for I. So I is equal to n minus 1. Once we get I, we want to plug this n minus 1 every time we see an I. So if we rewrite this again, we'll see n minus n minus 1 plus n minus 1 minus 1 plus some center stuff, and then n minus 2 plus n minus 1 plus n. So let's simplify these two. So what do we get with this? This is n minus n plus 1. So this is just 1, which we already suspected right here. What is this one? This is n minus 1 minus 1. We do a negative operation. This happens to be... So the n's cancel out and we're left with 2. And then this just continues on like this. So this looks a lot like the summation series, and if you don't know the summation series, there is a formula on the appendix, and it looks like this. And the solution to this is, what is this, n squared plus n? And when we do a big O, we only care about the variable with the biggest exponent. So if we have a really long polynomial, we only care about the variable with the biggest exponent. So we just delete all of this, and then we do a big O of n3. So in this case, it's n squared plus n over 2. We don't care about the constants. We don't care about the little n's. We care about the big n's. So the solution, the runtime of this summation is big theta of n squared. So this is also given in the appendix, but the problem wants us to get big O, not big theta. But if you remember from the earlier chapters, it says that if a function is big theta of g of n, this implies that f of n is also equal to big O of g of n. And this is because big theta is more tightly bound than big O. So big theta is both upper and lower bound, and big O is just upper bound. So whenever we get big theta, it implies that big O is also true. So big theta n squared means that big O n squared is also true.